everyone, this is Dr. Speranza and welcome to my YouTube channel. And if you happen to watch this video, you are in for more word problems involving calculus. So if you want to know how to use those complex implicit differentiation into word problems, then continue to watch this video, and you're gonna be with me in my class here in Marshall Community College to learn how to use implicit differentiation in solving word problems involving related rates. So we started with implicit differentiation last week, and today we're going to be diving into working or using implicit differentiation in answering word problems. So implicit differentiation, we'll start with the basic use of the implicit differentiation, and we know that in calculus, notations, symbols, and how we write notations in calculus is important, and this is going to help you answer word problems later on. So here we have a function 2x equal to x plus 2y, and we're going to find the derivative of this function with respect to the function x. So simply put, if we're going to answer or use our symbol or notation to answer this problem, we're simply finding the derivative of 2x with respect to x, and this is how we write it in calculus. d dx of 2x is whatever. We're going to be working on that in a little while. So if you can take the derivative of the function of 2x, we have three terms here that we can differentiate with respect to x, and it'll be d dx of x plus d dx of 2y. And now we know that we are just basically taking the derivative of 2x, taking the derivative of x, taking the derivative of 2y with respect to x. And for the first problem, the derivative of 2x is simply 2 dx all over dx. So technically, this is how the differentiation process works using the proper notation. In the same way, if we're going to find the derivative of x with respect to x, what is the derivative of x with respect to x? 1. So this is just 1 dx all over dx. Plus the derivative of the third term, which is 2y. What is the derivative of 2y with respect to x this time? It'll be 2 with dy all over dx. And in this case, notice that for this term and this term, dx all over dx is simply equal to 1 mathematically because they have the same numerator and same denominator, so it's basically equal to 1. So we'll just write it out as 2 equals 1 plus 2 dy dx, and the dy dx will stay because we can no longer simplify them. So this is basically how we're going to show the derivative of this function with respect to x, which is somehow similar to differentiating regular number, but this time we need to be a little bit more meticulous when it comes to writing out notation. All right? Okay, so in that case, let's say I have the same function, but this time you're taking the derivative of the function with respect to y. Can you please go through the process of differentiating this function with respect to y this time? So now we're going to write our notation as dy of 2x, right? Because we're taking the derivative of 2x with respect to y. That's basically what this symbol means in calculus. And this time we're going to take the derivative of x with respect to y and the derivative of 2y with respect to y. And by doing so, this will turn into the derivative of 2x, or regular 2x is just 2, but we need to include a notation which is dx all over dy, right? And this one will turn into 1 times dx dy plus, what's the derivative of 2y? 2 and dy dy, right? We took the derivative of y with respect to y, right? So that's basically how you should visualize the symbol in your head. This one, we are taking the derivative of 2x with respect to y. And the answer is, we took the derivative of 2 dx all over dx with respect to y. All right? And now, by simplifying the function, this is the only notation that we can simplify. So this is simply 2 dy. All right? It's still dx dy. It's not going to change. Okay? So this is the only one that is going to change. So we took all the derivatives of the function with respect to y. So if I have same function now with respect to t, can you please derive or differentiate your function with respect to t? And again, visually or in your head, you should be saying derivative of 2x with respect to t, derivative of x with respect to t, derivative of 2y with respect to t.
2 dy over dt.
Yes. Is there anything here that we can simplify?
No.
No. So that is your function with respect to t this time. So now that you know how to work out problems using the proper notations in calculus, it will greatly help you on working with related rates, because related rates are basically finding the derivative of a certain formula with respect to time, because this time we're going to be answering word problem. So in word problem involving related rates, we're going to compute for how fast something is growing, or how fast something is shrinking, or how slow something is, whatever movement we're working on. So related rates, it's all about movement in mathematics, because in geometry and in algebra, we are only limited to answering problems involving how big is the pond, or what is the volume of this box over here, something like that. But this time we're going to be working on how fast it's growing, how fast it's shrinking, and so on. So if I have this, which we did last week, let's see if this time you'll be able to answer this with confidence. If our function is y equals square root of x, and we need to find dy over dt when x is equal to 4, given that dx all over dt is equal to 3, how are we going to write this function? Your clue? How are you going to differentiate the function with respect to?
T.
Alright, do it right now. The problem a little bit more exciting. This is our problem. Suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when the value of x is equal to 1, given that dx dt is equal to 2 when x is equal to 1. So many math symbols, right? And so many x's and y. But what do you think are we supposed to be doing to answer this problem?
The
Derivative of what function?
y equals x squared plus t.
Yes. Derivative of the function y equals x squared plus 3 with respect to what function? Related to what? To x, to y, or to t?
T.
Related to t. That's why the clue is dt. And it's also here. Functions of t. So we're going to find the derivative of each term with respect to t. So we'll have d dt of y, d dt of x squared, d dt of 3. And now our problem is a little bit more manageable now, because now we have an equation to work on. So for the first function, what is the derivative of y with respect to t? 1. That's it.
dy dt.
If I forgot my dy dt, will it matter? Yes. That's why you cannot forget the dy dt because it's part of the solution of your work. D dt of x squared. So the derivative of x squared is?
2x
And it's
dx
dx dt. Plus the derivative of 3 is 0 with respect to time, so it's just going to be 0, right? Because any number multiplied by 0 is just going to be 0. So ultimately, we have a function now. And in our function, we can start plugging in the value that is given in the problem. And what's given? The x. What else? Dx dt, which is this. So what are we trying to look for? Dy dt. So plug in all the information you have in your word problem and you will find your dy dt. And in this case, it will be dy all over dt is equal to 2, what is x?
1
Times, what's dx dt?
2
2. So there. Plug it all in and you'll have your dy dt, which is 4. So in problem solving, especially calculus, sometimes it doesn't make sense, but if you know what you're supposed to be doing and just trust in the process, you'll be able to get somewhere. And that is basically what happened here. First, we need to figure out the function that is given, which is y equals x squared plus 3. The information that would help us find what we're looking for, which is dy dt when x is equal to 1. The given information is that we have dx over dt, and of course x is equal to 1. And by using the function x squared plus 3 or y equals x squared plus 3, we're going to find the derivative of this, derivative of that, derivative of this with respect to time. And by doing so, this will turn into dy over dt, or 1 times dy over dt. This will turn into 2x dx over dt, and the derivative of a constant is just 0. And now that we have an implicit differentiated function, all we need to do is to plug in all the values. For x is 1, and for dx dt is equal to 2. And now we have dy dt, which is equal to 4. Finish. Because I just want to show you that you need all these 3 things every time you're working with a word problem involving the related rates. You need to know your equation, which is this. You need to know the given rate. One of the rates will be given all the time. And what you need to find, which is here dy dt. So once you have organized all the things you need to use to be able to answer this problem, you're ready for your implicit differentiation. So, okay. Jessica dropped a pebble into a calm pond, causing ripples in the form of a concentric circles. Can it be can it be squares? Obviously not. The radius r of the outer ripple is increasing at a constant rate of 1 per second. When the radius is 4 feet, at what rate is the total area of the distributed water changing? So, remember how we did this last week? Okay. According to my graphic organizer a while ago, you need to have an equation, you need to know your given information, and you need to know the given rate. What is the given equation in this word problem? Is it explicitly given in this word problem? No, the equation is not given in this problem. But we have a clue that would help us use an equation that we could use to answer the problem. And what would that be? What is the clue in this problem?
The rate.
The rate, what else? What is it that is forming here? The circles. And what are we looking for? Total area of that circle. So that means, what do you think is the equation that we're going to be using in this problem? Area of a circle. Alright, here we go again. What is the area of a circle?
Pi r squared.
pi r squared?
Yes.
I was gonna say 2 pi r. Wait, no.
When it's an area, it's the square. Since the circumference, there's a number 2. All right? I mean, that's how I remember it. So the area of the circle is pi r squared. And now, all we need to do is to differentiate this formula with respect to time, because that's basically what is happening here. You are trying to figure out what the rate at which the total area of the distributed circle is changing. And to do that, we're going to be differentiating with respect to time, seconds, right? So we're going to take the derivative of A with respect to, and we're going to differentiate this function, pi r squared, with respect to t. Now we're going to be using the constant rule, and the constant rule is ignore the constant and focus on the function. What is the constant in this function? Pi. So I'm going to rewrite my derivative, d dt of A equal to pi, set it aside, d dt of r squared. And now we're ready to differentiate. So what is the derivative of A with respect to time? dA all over dt. Pi is outside, so what's the derivative of r squared with respect to time?
2r dr dt.
And now we have the derivative function, or the rate of change function. So now we have the change of the area with respect to time, and the change of the radius with respect to time. All we need to do is to plug in whatever it is that we could plug in. What are we trying to look for first?
The rate.
The rate of what, or the total area of A that is distributed with the water. So which one are we looking for here? dA over dt, the r, or the dr over dt? Are we looking for the rate of change of the area or the rate of change of the radius? Yes. dA all over dt equal to pi times 2 times what is r? 4. And what is dI over dt? 1 foot per second, so it's just going to be 1. Right? Alright. Feet per second. Got it? Alright. So this is how we find the related rate problem given the information we have, for this equation. So the equation is the area of the circle, and the given rate is 1 per second, and what we need to find, which is the total area of the disturbed water changing when r is equal to 4. So it's going to be dA over dt. So once you have organized everything, you need to do calculus, because now you can take the derivative of the equation with respect to time. ddt of A, ddt of pi r squared is simply dA over dt, and this one is going to be pi d dt of r squared, which is 2r squared, right? I mean 2r, right? So we'll have 2 pi r dr dt, and then from the given rate and what we need to find when r is equal to 4, all we need to do is to plug in the values that's in the problem. And in this case, r is 4 and dr over dt is 1. So the rate at which the disturbed water is changing is 8 pi for this particular problem, with the unit of measurement that is feet per second. So when the radius is 4 feet, the area of the disturbed water is changing at a rate of 8 pi feet per second. George is inflating a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Now, do we have the equation that we're going to be working on in this word problem? Yes or no? Is the equation explicitly given in this word problem? Yes or no? No. But what do you think are we finding, or what clue can we use so that we can find the equation that we're going to be using in this related rate problem? maybe we're looking for a sphere or using the formula for finding an equation that is related to a sphere, right? So,
Seems like it.
do you know the formula for finding the volume of a sphere? That is why calculus can be extremely difficult if your math fundamentals is a little bit shaky. Algebra, geometry, trigonometry, statistics, maybe. But those basic disciplines or disciplines in mathematics, you need to know how to use them in calculus. Alright, since you don't know, I'm going to just give it to you. The formula for the volume of the sphere is this. Copy it down. Now you know. Alright, so now that we know the formula that we're going to be playing with, we know that we're going to be differentiating with respect to time, right? So you already have an idea of what we're going to be doing afterwards. But what is the given rate in this problem?
4.5 cubic feet per minute.
Yes, that is the given rate. 4.5 cubic feet per minute, or 9/2, or 4.5. Just stick to 4.5. And what do we need to find? dr over dt. Right? Rate of change. They are changing, so it's dr over dt. Differentiating your radius with respect to time. When the radius is at 2 feet. Okay, now that we have organized all the equations that we're going to be using, can you take a shot and see how you're going to answer this problem? And now we're going to find the derivative of the function. So now that we have our equation, our given rate, and our dr dt, so we're getting the derivative of the volume of the sphere, which is given by 4/3 pi r squared. And we're taking the derivative of this function with respect to time.
R cubed.
R cubed, not r squared. And by doing so, we'll do the derivative of v with respect to time. And we're going to be using the constant rule. And can you please tell me the constant in this function that we can ignore for a little while?
4 pi over 3.
Yes. 4/3 pi or 4 pi over 3. So we'll set it aside and just focus on the derivative of the function r cubed with respect to t. So now we have the derivative of v, which is dv all over dt, equal to the constant multiplied by the derivative of r cubed with respect to time, which is 3r squared times dr over dt. And now that we have our formula that will help us answer the related rates problem, all we need to do is to plug in all the information that we have in our problem. And what can we plug in?
2.
dv over dt is given, right? What else is given? R equals 2. And what are we trying to look for? And that is what we're going to isolate later on. So let's substitute 4.5 equal to, let's simplify this function. Can we simplify this? Yes, right? We can cancel the 3. So we're only left with 4 pi times r squared times dr all over dt. And what is r?
2.
R is 2. So by simplifying this further, we'll have 4.5 equals 4 pi times 4, right? Times dr all over dt. And now we have 4.5 equal to 16 pi times dr all over dt. Right? Yes. So 4.5 all over 16 pi is our dr all over dt. And since dr over dt is the rate of change, what will be our unit of measurement for our answer? Can we simplify it further? Yes, if we are going to use a calculator, which I have right here, let's see how we're going to find its 0.0895. Take the derivative of the function with respect to time for both function. So now we have dv over dt. The constant is 4 over 3 pi. So we'll have the derivative of this function, which is r squared, or 3r squared. We canceled out the 3, and we have 4 pi r squared dr dt. And by plugging in the value from our equation, dr over dt is going to be 1 over 4 pi r squared dv dt, which is 4.5. So our function will give us, which is the same as what we have a while ago, right? 0.089 something. So that is how we use the related rates problem in answering problems like the inflating balloon. So we had area of a circle, volume of a sphere, right? Let's see what our next problem would be. So in our answer, George's balloon being inflated with a radius of 2 feet is expanding at the rate of 0.090 feet per minute. It was minute, the unit of time that was used in the problem. I thought it was seconds, but this is how we're going to be using our equation. All right, your turn. On your own. A spherical balloon is inflated again. We love balloons in calculus. With gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing at that instant with a radius of 30 centimeters? Okay, do this on your own. See if we did it right? Hopefully we did it right. So the formula is 4 over 3, 4 pi r squared. Take the derivative of each term. Use calculus so that we can find the derivative that we're looking for, which is this time dr over dt, which is 800 over 4 pi times 30 square. And using the calculator, dr over dt is going to be 0.071 or 0.070 something else. And the unit of measurement is going to be centimeters per minute. And if you happen to like this video, please like, share, and subscribe to my channel. And watch out for more videos on my upcoming series and features. And again, thank you so much for watching, and see you all next time. Bye.